if you want to bring up your presentation, feel free to begin whenever you're ready.
So you see the full screen?
Yes.
Yes.
Right. Okay, thank you very much for the invitation. So as stated in the title, that I will talk about what we know about the organic content coming out from Enceladus subsurface ocean, or let's say from Enceladus subsurface. So let's begin with a brief introduction about Enceladus. We know that this body has a global subsurface ocean, which is in contact with the rocky core. And then we have the icy surface on top, which is a bit thin on its north and south pole, particularly south pole. And there we have the geysers and the plume coming out from the cracks within the icy crust. So there is a hydrothermal activity that we think that is happening currently at the ocean floor, where the water is percolated in the rocky core, and then we have a lot of chemical reactions, exothermic reactions, and as a result, we have the material coming out all along through the ocean and then finally out of Enceladus. So that means so far, whatever we have found through the hydrothermal activity all along through the ocean and travel across the icy crust and finally in the form of plume of gas and ice grains, we have a lot of organics that we have observed. So this is really organic enriched plume that we are talking about here. And I will update you that what kind of organics that we have so far and what are the upcoming organics on the way of the discovery. So this is important here to understand that where we normally measure the material which is coming out from Enceladus. We have this Saturn on the right top, and you can see the diffuse E-ring around the Saturn. And here in the vicinity, in the orbit around the E-ring, we have Enceladus, which you can see on the left side, which has the activity. And on the right bottom, you can see from the South Pole, the plume is coming out from Enceladus. So we measure this material not only directly into the plume, but as well as we measure this material within the E-ring as well. So this point is also needs to be considered here, that flyby are important to get the freshly ejected material, but at the same time, there are free sample which we can collect in the E-ring in the form of ice grains. So two mass spectrometers that we have on board Cassini, one is INMS, and which is actually sensitive to measure the neutrals and the gases. And we have almost the latest number, or maybe there is a little bit change, but of course 96 to 98% we have water, CO2, methane, ammonia, and molecular hydrogen. But besides that, INMS also detected some other smaller compounds, which we can say that the volatile compounds from C2 to C3 hydrocarbon species, as well as nitrogen and oxygen bearing species. At the same time, CDA, which is the cosmic dust analyzer, it measures actually the ice grains directly through the plume and also in the E-ring. So far, if I divide into the category of the ice grains that are coming out from the Enceladus, then there are three types of ice grains. And we are really interested actually, which I highlighted here, organic enriched, which we call as type 2 grains. Most recently, Peter and colleagues actually found this hydrogen cyanide, which is long-awaited species to be confirmed. Earlier, it was ambiguous in the INMS results, but now the recent paper, which is in archive, this species, and along with this hydrogen cyanide, more species also found and confirmed through INMS data evaluation. So I will talk about more on the ice grain part of the plume, which actually measure through the cosmic dust analyzer on board CDA. The very basic principle is that we have ice grains at a certain relative velocity. The ice grain enter into the cosmic dust analyzer, it hit to the target metal, and then it vaporize and ionize. Here I will try to, if I can run this simulations here, but unfortunately I can't. So here is the cartoon of the cosmic dust analyzer where the ice grains actually entered here, and upon entered, it is shattered and ionized, partially vaporized and partially ionized, this material, and that material is actually collected to the multiplier, which is the mass spectrometer here, and then we get the compositional information. The point is here that we are blind for the negative ions here with cosmic dust analyzer, so we only measure the positive ions, and then we get the mass spectra here. And those mass spectra we evaluate, and of course, we need some analog experimental setup where we can confirm what we see in the mass spectra. And this is the analog experiment, which we call laser-induced liquid beam ion desorption, where we actually prepare the proposed sample and then we shot infrared laser. And the similar mechanism we achieve what we achieved normally through CDA impact, and then we measure the cations. This setup also measure anion, which is for the purpose of Europa Clipper, particularly for SUDA, and we are building the spectral library for that purpose as well. So this is the spectrum, the general template of the spectrum, which comes from the space. And this is the spectrum of the ice grains, but the ice grain which carries actually organics. And in this spectrum, you could see that we have a lot of water cluster features. This is the way that how we identify that what kind of species are there. So because it's a water ice grains which carries organics, so we have water features. But besides water features, we have very characteristic feature of organic enriched spectrum, which is actually this mass line, which is between 26 to 31 mass units. So in this mass unit, we have a lot of species that characterize to the organic material. And once I have described that what kind of spectra we are looking for through impact ionization mass spectrometry, then the very first major results that we have regarding organics is the high molecular mass ions that we have found in these spectra. If you look at the left top bottom, then this is a complex kind of mass spectrum. Important is that you see this species that is here about 77 and 78, which is actually referred to as benzene cations. And then if you see on the right side, you will find a sequence of mass lines with a certain mass differences in between. So that means that the consecutive mass lines has the mass difference approximately 11, 12, 13, and 14. So it means that we have unsaturated and saturated fragments here. So this actually allows us to characterize that what kind of organic material is. One characterization we could do from the benzene cations, and the second one characterization of the material which produce this kind of spectrum is this feature, which we call HMOC series. On the bottom, you can see that how above 90 mass unit, you can have the different differences in between the consecutive mass lines, which tells you that they are unsaturated fragments. These species are about 200 atomic mass unit, more than 200 atomic mass unit. concentrations are on the percent level. We have aliphatic and aromatic constituents here. The functional groups could carry oxygen and nitrogen, and they are poor in solubility, poor in water soluble. Besides this fragment, we could stretch our mass scale, and we found that in the extended mass range, we have here the features which are of course very poor in resolution, but still we could identify that they are, this material has much higher mass value as compared to the 200. So we assume that it goes to 2000 mass unit. So it means it is really gigantic material that we have found. And what kind of characterization based on the spectral evaluation? We think that the material that we have seen here is somehow multiple aromatic ring structures with the crisscross of aliphatic chains, aliphatic hydrocarbon chains, as well as oxygen and nitrogen species in it. So this is our kind of I should not say that the speculation, but of course we don't have the much better choice than such kind of material which is crisscross with hydrocarbons and aromatic species. Then in the subsequent discovery, we have found the low mass organic material. So the low mass organic material has its own significance if we have that in Enceladus ocean. So low mass organic material has three categories. One is the aromatics. And I would take you again on the left top, this is the spectrum from the space. Again, I would like to show you this peak, which is the benzene or the phenylcation peak. But you can see that there are no feature on the right side as you have seen in the previous high mass organic spectrum. So it means that here we are looking at the material which is aromatic for sure, but which is not the large, the high mass, which is approximately less than the 100 mass unit. And we have mimicked this spectrum in the lab by using this kind of compounds, benzoic acid or the benzyl alcohol. And you could see that we have matched the fragments 77, 63, 51, whatever we have seen here. And we constrain that what kind of organics they could be. For sure, they are aromatic, but they are aromatic, which is singly ring aromatic compounds along with one functional group, which could be hydrocarbon, which could be hydroxyl, or which could be carbonyl. So this kind of compounds we have seen here. Then the second low molecular mass is carbonyl group, means the double bonded oxygen group. So this is again the spectrum from the space, and on the right side the spectrum from the lab. And you could see that ignore all blue lines, they are the water clusters, but the green one is the spectral species that we have identified as acylium cation or the characteristic cation which we can get from the carbonyl compounds, and we successfully matches that. And we propose that these are again this low mass value. Low mass means about less than 100 mass unit, and we propose that these could be such species which are listed here, including pyruvic acid probably and many others. Then there is the third category, which we call as amines. We have found N-bearing species, N-bearing aliphatic. And again, you see on the left top, the green lines are the characteristics, which are the characteristics of amines. We have Mayer's here, butyl amine here, and you could see that we have successfully matches the representative peaks. And again, the structural constraint that we apply is methylamine or ethylamine kind of compounds. So these are the three categories that we have found. So in a summary of these compounds, on one hand, we have high molecular mass refractory organic material, which is way above 200 mass unit. which is kind of the combination of aliphatic and aromatic constituents with the functional groups carrying oxygen and nitrogen, and poor soluble. On the other side, we have low molecular mass in the ice grain that we have found is less than 100 atomic mass unit. Concentrations are ppm to percent level, mostly aliphatic, polar functional groups, amines, carbonyl, ethoxy, and they are soluble. So these are the two variations that we have. And just for the significance of the low mass that we have found, I mean, the nitrogen bearing aromatic and the oxygen bearing compounds, that in Enceladus case, in the ocean, if we have the clay minerals there, then these compounds we can call these compounds as the building blocks of some life originating or the biogenic kind of material that these compounds can react together with clay minerals, and then finally they can form such compounds which are biological relevant compounds, I would say. How they work, for example, we have low mass oxygen bearing compounds, and if in the presence of those minerals they can do alkylation, then we have hydrogen and amination process, and then finally we can get aromatic amino acids. This is the example of proteogenic amino acids here. Similarly, if we start with the low mass oxygen bearing compounds and we do amination and reduction properties there, then they could form low mass carboxylic acid that we proposed, as well as they can form the amino acids. So such kind of reaction schemes we just proposed based on the people who have worked on the hydrothermal chemistry quite intensively. So the question is that how this material actually come up into the ice grain. On the very left side, this is the cartoon where you can see that this is the ice shell, and in the ice shell you have the water rising there, and then this is enlarged here in the panel A. What happens that we have volatile gases, and these volatile gases are coming through from the water surface within the icy vent at triple point temperature pressure conditions, and we have a lot of water vapors and lot of volatile organic compounds, and they actually condensed during their travel outside Enceladus, and they form the ice grains. So you can see that what kind of volatiles, which I just explained, that nitrogen bearing, oxygen bearing, aromatic, and sometimes they are mixed together. So these kind of ice grains, which we call type 1, which is pure water, and type 2 VOC, which we call organic, but they carry volatile organic species. But there is other type of organic that I just explained, which we call type 2 HMOC, means high mass organic. And the basic fundamental principle we think is the bubble bursting. The volatile gases are coming through, and we have the layer kind of, or the patches of you can say that it's not mixing material, which is here at the top. And when there is a bubble of gas burst here, then you get the aerosols as well as the droplets of the organic material. And this organic material, which is in the orange color, carries up, and then the water condensed on top. Also, it could be possible that there is also the condensation of these volatiles onto the HMOC kind of material, and then they form ice grains. Of course, there is also salty particles, but this is not the subject today. So these are the material that we get out of Enceladus in the form of ice grains. But then we still have the hunting for the new organics coming out from Enceladus. On the very left side, you can see a plot. And this plot is by the data evaluation of E17 flyby of Cassini. I think it was in 2015. And what I did here is that I evaluate the ice grains composition, and then I draw the profile. And I found that from the from the left side, you are approaching to Enceladus. So this is the closest approach, 0.0, which is right above the tiger stripes. So when you are right above the tiger stripes, you see that these yellow line, which are rising here. So it means the abundances of these organics are really increasing. So we have really organic enriched plume here. On the right side, this is the latest work in a few days back came out, where INMS data evaluation has been done from E14, E17, and E18 flybys. And there are new organics have been found. For example, this is the new list of INMS organic, which are on the very top, it is confirmed. And in these species, I particularly highlight C3H6 because it is here where INMS result matches the tentative results from CDA, which I will show you in a couple of slides. So this is alkene, C3H6 is alkene compound, and this is also this also provides some unique information about Enceladus hydrothermal vent. You see here in the previous slide, I just mentioned INMS result about the new species, but here I am back again on CDA results of the new data evaluation, which is actually the E5 flyby. This flyby was done in 2008, and I started to re-evaluate of this data. Why? Because this data provides the freshly ejected ice grains, and I thought that we should really look into this kind of data. Maybe we find some new species here. And this is the very first kind of, its own kind of spectrum that I have found the very first time. And further evaluation which is in progress, but here I assume it's a tentative result, but I think that these are the features which are actually relevant for corresponding to alkene compounds. So these are the compounds that CDA also observed here in this particular ice grain, and which is C3 to C4 species here. And that means whatever an INMS has seen there, the alkene compound, and they confirmed, probably CDA also see in the ice grain these compounds. And this has implication that I will show you in one of the slides. This is, I think, 2 to 3 slides are remaining now. So this is another new type of organic where the very first time I have seen such kind of features where we have this mass line at 59 to 60 conjointly with 31. And when I evaluated this spectrum, then I dig into a lot of data banks which has mass spectrometers, mass spectra, and the candidate compounds that I think are this kind of, which is diethyl hydrazine or ethyl ether or dimethyl ether, which carry oxygen here. And this has a huge implication together with alkene compounds that I have showed you previously. What is the implication here? The implication of finding alkene kind of compounds or ether compounds from CDA, from Enceladus, is that if these compounds are there that I showed you in previous slides, then it means that there is a mechanism going on in hydrothermal, Enceladus hydrothermal, because we have methanol there. Suppose that we have clay minerals there, and in the core, in Enceladus core, we have the temperature between 200 to 350 degree. I'm not talking about the ocean floor, where the temperature is 90 degree, but more deeper into the core. And then there, because of these hydrothermal alternative pathways, we can produce CH4, CO2, dimethyl ether, C2 to C6 alkanes and alkenes. And CH4 we have found, CO2 we have found, and now if this is true, what I showed you in previous slides, then we have found the ether compounds and alkenes. And these provides the further synthesis within the clay cavities of the hydrothermal chimneys, where we can find further bigger organic molecules. So it means that apart from Fischer-Tropsch reaction, that is characteristics also for hydrothermal, we have another alternative pathway based on what we have found. And with that, I think what we have seen is just a tip of organic iceberg. And that means that there is a lot to discover. And in the recent analysis of freshly ejected ice grains, I think we have confirmed what we have seen already in the previous work. So with that, thank you very much.
Great. Thank you, Nozair. We'll hold the questions until we finish the second presentation by Shannon. So Shannon, whenever you're ready, feel free to start.
Okay, sharing screen and starting presentation. Good.
Looks good.
All right. I have to thank Nozair. I was hoping that he would give a great introduction to all of the reasons why we want to go back to Enceladus and look for signs of life, and he did. I hope you guys are all on board with all of the rich potential of Enceladus as a habitable world established by the Cassini data sets, like what Nozair was just showing us. So if that's true, if we can kind of check all of those standard boxes for Enceladus, that there's liquid water, there are energy sources, there are these chemical ingredients for building blocks, then we're really ready to ask the next question at Enceladus, which is that habitable environment inhabited? So as part of the decadal preparation for the decadal survey for this decade that we are now living in, NASA put out a call for teams to propose different, mission concept studies that we should do. And our team said, hey, if we went back to Enceladus, specifically with a flagship class mission, so just a reminder for all of ourselves that the flagships are the largest class of mission that NASA does. It's directed, so the instruments are competed, not the mission itself. And those come from decadal survey recommendations. So we targeted specifically that class to ask what a mission concept of this class would look like in the coming decades. So not relying on too much technology that's down the road, but more, the stuff that's already flown or being developed in programs like Matisse and Picasso. So the first thing that we did to figure out what a mission concept like this would look like is start with the science. And we said that our priority was going to be searching for signs of life in the Enceladus plume material. And there were about 12 of us in the room. Some of those fantastic folks are on this Zoom room today. And I'm sure if there were a different group of 12 scientists, we might come up with a different list of measurement priorities. And that's okay. This mission concept that I'm describing is not meant to be the end all and be all of how one should go back to Enceladus, but rather a demonstration of how we could do it. So these are the biosignatures that we put together for our mission concept. And you'll notice that we kind of grouped them into two categories. One was the chemical biosignatures. This, to me, is kind of the bread and butter of where we're at with biosignature detection. We're really confident in our ability to do things like amino acid and lipid characterization. But they're a little bit harder to get up on the podium and tell our family members and the rest of the world, like, hey, we found life because we found these amino acids and they have this different handedness. Isn't that so cool? That's a harder story to tell. So we also included these what we called confirmation biosignatures, something like being able to detect something like DNA, a genetic biopolymer. That's something people really grasp onto. Or even if we were able to characterize and image something like a cell. So those are a little bit higher risk, but potentially higher reward. So we tried to include both philosophies in our life detection strategy. This naturally led to a payload of instruments. You're seeing the suite that we put together here. Again, these are not the only instruments one could go back to Enceladus and look for signs of life with, but we tried to make a payload that was representative of some of the current technologies, which are kind of on the left-hand side, and then technologies that are coming up or are really advancing in their development. That's as you move to the right-hand side of the slide. So another part of the philosophy of the biosignatures that we put on our list was that we were trying to build a set of measurements that would be complementary and orthogonal in our characterization of that plume material. This is an attempt to build up our robustness to the difficulty in making these measurements, whether there's not enough biomass in the plume or not, for example. So we thought that that was a really important thing for any mission concept moving forward at Enceladus to remember to consider. All right, so since we were looking at a flagship class, we also thought it was really important to take advantage of those additional resources that one has at that flagship class. And so we tried to fit in as much context measurements as we could without going overboard to provide the context of, these bio potential and chemical measurements that we're making. How does the physics of ejection affect the plume particles, for example? How does the geology affect how how the surface and the vents are interacting? So those kinds of scientific questions are really key, we think, for interpreting some of the measurements that we'd make with the life detection suite. And lend themselves to a more traditional set of instruments that you might expect on a spacecraft payload. And I won't talk much more about those because this is the network for life detection, but here is the full payload suite in its entirety. You'll notice that they are broken out into orbit, surface, and both. So let's dive into the etymology of Orbilander. This one spacecraft serves as both an orbiting spacecraft and then a landed spacecraft. And this is because Enceladus is so small, being only 500 kilometers in diameter and then orbiting around a massive gas giant like Saturn means that getting into orbit is the more difficult part. The orbits, during the orbital phase, we'd be doing science as we're passing through the plume. We'd be running collecting material to run all of the life detection suite payload elements except the nanopore, because we think that that's going to require too much sample for what we can acquire in orbit. Oh, did I freeze for everyone? Am I back? No, I only froze for myself.
You're good. You froze briefly, but you're good now.
Okay, great. Thank you. One of the advantages to being in orbit is that you have access also to the vapor that's coming out. So that's the material that INMS measured. And also being in orbit is where it's easier to do global and regional mapping with instruments like a camera or an IR spectrometer or even a radar sounder. So that's the science that we'd be doing in orbit, and those latter measurements are what we would use to identify a safe landing site. So this is what the orbits look like, or what the orbits could look like. We use the top half of the ellipse in that kind of orange section for doing the station keeping maneuvers that we need to maintain our orbit around Enceladus because it's such a tiny body and getting tugged on by Saturn. Then as we're coming closer down at the bottom of the ellipse is when we start to turn the spacecraft and prepare it to collect the plume material with a passive sample collection mechanism like a funnel or a plate. Once we've identified a safe landing site, and once we've convinced ourselves that we're finished with our interrogation of the upper parts of the plume, we then can spend the rest of the mission on the surface. So we get ourselves down onto the surface. We have to shed just like 200 meters per second of orbital velocity, which is, in the grand scheme of things, not that much. Once we're on the surface, that we can continue to use that same plate or funnel that we use to ram through the plume and collect particles. That's our passive sample collection mechanism. Use that same thing to just sit on the surface and collect plume particles as they fall down. But we also included an active sampling mechanism, and this could be something like a scoop or a rasp, or something like pneumatic transfer, more like a vacuum, to actively interrogate the surface. So that allows you to collect a lot more sample and run really sample intensive analyses, like something like a nanopore sequencer. The context measurements on the surface include seismic monitoring and then context imaging of the immediate surroundings and the samples in front of us. So again, to summarize, Enceladus Orbilander is just one spacecraft that first orbits and then spends time on the surface. This is how we divvied up the CONOPS, but the beauty is that there's some wiggle room in that 1.5 years in orbit or 2 years on the surface. If it takes us a little longer to identify a safe landing site, we spend 2 years in orbit, there's still time to do all of the science on the surface. So why did we break it up this way? Like, why even bother getting down to the surface if you have the plume? Well, the advantage of those additional resources of flagship is that you can take full advantage of the plume. So up at the higher altitudes where you're orbiting, you're getting the vapor from the plume, and you're getting micron to maybe nanometer size ice grains. But the largest particles in the grains or in the plume are not going to make it that high. Instead, they're going to fall back down onto the surface. And based on the Cassini data, which kind of suggests that those larger organic content will track with the larger grains, we wanted to get at those larger particles. And so that's why we're trying to get down to the surface. But that doesn't mean that we should ignore the plume. I think there's a real advantage to being able to first fly through and then catch and scoop. Then you can make a comparison about what the different particles and their different compositions might be telling us. That's also a difference in how much material you can acquire. So in the fly through, depending on how well you can aim your spacecraft, so that's another important part to this. You are, collecting on the order of microliters, maybe. And again, we were trying to make conservative estimates to make sure that this is a possibility that we're building a mission that's possible. But then once you're on the surface, you have, depending on where you land, access to a larger collection of material, either by the passive catching or active scooping or rasping or something like that. So altogether, we thought that this balance of sample collection mechanisms and biosignature investigations would make us robust to life detection at levels up to 500,000 times scarcer than Earth's. And that really lies in our calculation of the limits of detection of different instruments and our expectation of biomass in the plume relative to how much material we're actually collecting in each of those sample collection techniques. But of course, we're also doing context measurements, which I think are important for the holistic view of Enceladus. The concept study outlined this timeline where we would arrive to Enceladus in the 2050s, which is when Enceladus' southern hemisphere would be coming back into southern summer, so that sunlight is starting to arrive at the South Pole. And I'll leave you with the conclusions of the Planetary Science Decadal Survey, which was that the second highest priority new flagship was listed as Enceladus Orbilander. that's very exciting, and I hope to see something like Enceladus Orbilander take place. But there are things ahead of it on the list. So I think it's also important to remember that Enceladus is also listed on the New Frontiers calls. And I really appreciate that the Decadal Survey panel took that into consideration, that there are ways that we could envision doing something like Orbilander, or some of the science that Orbilander is going after, perhaps on New Frontiers. So they left that call open. And I'm really excited to see what the decade ahead has for Enceladus exploration. So I'll leave it there, and with a thank you to all of the Enceladus Orbilander team members from the science team, including the APL Mission Design Lab. Thanks very much.
Those are excellent. Thank you so much, Shannon. I believe we're going to wait 1 second while Bradley turns off the recording. Are we good, Brad?